Hello everyone, welcome to Agar Mudal YouTube channel. This is Arun. So I would like to apologize to everyone. In the last video, there was some hiccups. So it might be reason that that was the first time in front of camera. Though I had experience in front of 60 plus students, so it makes me feel in front of camera while I'm standing there. So it makes me feel that I'm speaking myself. So that is the reason why some hiccups happens, and there are some feedbacks regarding that blur in the boards, so which will gives us very much of motivations and good suggestions, so which will makes me to improve myself in the upcoming videos. So I would like to ask all the peoples to continue this kind of supports in the future, and the aim of this channel which was opened is to get the help, to give the help of all the competitive exam aspirants. So there won't be any hiccups hereafter. So you will get received the content which you are required with crystal clear in nature. So there is no further delay. We'll get into the our video. So as I said in the last video, so we are discussed about reinforced cement concrete. So the first one is introductions. So whenever a structure, all the more or less all the components of the structure is made up of reinforced cement concrete. So here we are going to see why that was used as a reinforced cement concrete. Before that, when we are saying concrete, there are two types of concrete generally we spoke about. One is PCC, plain cement concrete. Another one is RCC, reinforced cement concrete. So generally PCC in the form of above the bottom of the in the form generally PCC lays at the bottom of the foundation to leveling purpose. But for most of the components like slab, beam, column and foundation itself, so we are using RCC, so reinforced cement concrete. So PCC, when we are saying PCC, plain cement concrete, it's a hardened mixture of cement, fine aggregate, coarse aggregate and water. So all the ingredients having some set of specifications. There should be some limitations. So we should take as per the specifications. If not, there will be some ill effects happen in the concrete. So first of all, we see what are the specifications which is required for the plain cement concrete. Then we are going for RCC type. First one, in a PCC, the major important one is cement. It is also called as binder, which binds all the ingredients of concrete. So cement generally of 75 mm to 90 mm micron. Cement size should be 75 to 90 mm micron. If it's getting excess of 90 micron, there will be segregation happens. If it is less than 75 micron, it requires much amounts of water which gets evaporated during the curing time. So we should keep the size of the cement as 75 to 90 micron. The steel generally available is 33, 43 and 53 grades. General grades of steel is available is 33, 43 and 53 grades. Nowadays there is no 33, and some laboratory purpose alone we are getting 43, and remaining all shops are available 53 grade, even that contains of fly ash content. So it's also called as OPC. Sorry, PCC is nothing but porcelain cement concrete. So sorry for that. So OPC, ordinary Portland cement. So these all are grades of ordinary Portland cement, and even nowadays we are getting PPC, Portland Pozzolana cement. In other terms, pozzolanic Portland cement. So what is in that? So 25 percentage of at the extent 25 percentage of fly ash covered with that OPC cement, and it makes it PPC. Right? Next one, fine aggregate. So when we are saying fine aggregate, usually we are taking natural sand. Natural river sands we are taking as fine aggregate. But nowadays there is a scarcity, there is a large demand on sand. So we are going for that M type of sand, crusher stone sand, that type of sands instead of natural river sand. But in general, for natural river sand, the size should be 2.36 mm to 4.75 mm. And another thing is coarse aggregate. When we are saying coarse aggregate, this is the major impact created on the strength properties of the concrete, which contributes 80% of strength in concrete structure. So it should be within the specified size. The size of the coarse aggregate should not be greater than 1 by 4th of the thinnest member. So when we are planning for designer components, so wherever the thinnest thickness available, it should be less than 1 by 4 times of that thickness of the thinnest member. And if we are using, instead of cutted rock, we are using stone chips. So there are two conditions are available. One is minimum spacing of the structure minus 5 mm, and another one is it should not be greater than minimum clear cover minus 5 mm. Whichever greater, we take it as the size of the stone chips. And in general, for RCC, we are taking 20 mm size coarse aggregate. So nowadays, wherever you can see, so you will see 20 mm size of the coarse aggregate. And if we are using heavily reinforced structures like dams and bridges, we are using 10 mm, because all the, if we are using heavy reinforcements which carries the large loads, so 10 mm is sufficient in that heavy or mass concrete structures. And for lean concrete, wherever the material quality or material size is getting lesser, those places we are using 40 mm coarse aggregate. So these all, and water, the important property of water which contributes the harden. So after adding water, only the heat of hydration takes place, makes the concrete binder and makes the hardened material. The water we are using for concrete should be greater than or equal to 6 pH value. So there should not be less or more impurities than this. Next, the most important one, why RCC? So we are using PCC. So in not very familiar places. So we are going RCC in almost all the structural membral portions. So why is that? The reason is that when we are saying PPC or OPC, or OPC, strong in compression. So compression is nothing but the vertical load. The resistance against vertical is called as compression strength. And generally that OPC strong in compression, but it's weak in tension. Whenever the lateral loads arises, it can't bear the lateral loads, it will be brittle. So in that portions, so we are using one additional member for that in lateral reinforcements or lateral forces, so in the form of steel, this is called as RCC. So to resist the tension creates in the structure, we are using steel as a reinforcing materials. So why steel, why not other material? So it is also having some physical properties which is more similar to the one of concrete. So what is that? The thermal expansion of concrete is 11 into 10 power minus 6 degrees Celsius. Our steel also almost similar to that thermal expansions. So whenever they are interacted, whenever they are binded one another, the friction won't takes the thermal expansions. So that is the reason why we incorporated steel in a RCC structures. And there are IS 456 which 2000, which was currently is in use of plain and reinforced cement concrete structures. So there was a code which was proposed in 2019 IS 456 2019 is proposed, but yet it was officially announced. So as of now, we are using IS 456 2000. So in that code specifies steel as three types. So what are the three types? One is Fe250, in other terms called as mild steel or plain bar. There won't be any deformations. The bar gets straightened. It should be flat. So that kind of bar is called as plain bar or mild steel bar. In other words, Fe250. So it denotes, and the specifications and its property details are shown in IS 432 codebooks, and IS 1786 its codebooks used for deform bars. So what is deform in the sense? The bar is not flat one. So there was some deformations which was created on the bar, which creates strong binding with the concrete portion. So IS 1786 is for deform bar or HYSD bar or Fe41 steel bar. HYSD in the expansion is called as high yield steel bar. High yield steel deform bar is called as HYSD bar. And also it is a code book denotes Fe500. So it is also called as HYSD bar, high yield strength deform bar. So we seen as per IS4 Physics 2000, we seen that there are three types of steel available. One is Fe250, Fe415 and Fe500. So based on that, the strength properties get differ. So in this table, we can see that for Fe250, we are comparatively give the all the properties, strength properties like yield strength, maximum tensile strength, and maximum compressive strength, and bond effects in the three distinct steel components. So one is if at Fe250. So I already spoke about that yield strength. So the point where the cracks or where the failures initiate, it's called as yield strength. So Fe250, the 250 is called as yield stress of or yield strength of steel. So in other terms, it is called as characteristic strength of the steel, and maximum tensile stress at the component. So tensile strength, it's occur at the tension zone of the structural component. The tensile strength he given us both WSM and LSM method. So we'll discuss about this later. So what is WSM is nothing but working stress method. So this method uses only design loads. It's nothing but safe loads. And in limit state method, the load taken as that collapse load or ultimate load. So we consider both WSM and LSM method. The maximum permissible tensile stress is which is nothing but which is nothing where it is applicable is beam, slab and foundation. It is applicable at the portion of beam, slab and foundations. Here at WSM method, the value is 0.56 times of yield stress. So yield stress that 250, so 0.56 times of Fi equal to 140 MPa for Fe250. Sigma St denotes as sigma St. The maximum permissible tensile stress sigma St equal to zero point 0.5 times of Fi for Fe250 grade steel. So here 140 MPa, if the diameter of the bar we are provided is less than 20 MPa, so it take it as 140 MPa. So if we are going the diameter bar greater than 20 MPa, so which was seen in the previous discussions, that at mass concrete or heavy reinforced sections we are going to use reinforcements of 10 mm, which is very much of lesser 20 mm. For lean concrete we are going to use of coarse aggregate 40 mm, and whereas same the reinforcements also getting differ. In the mass reinforced structures, the reinforcements is more than 20 MPa. Those places that sigma st value 130 MPa, and in limit state method it denotes as the yield strength divided by factor of safety of the steel. What is 1.15 is nothing but the factor of the safety of yield stress based on limit state method. So in short form, we are getting 0.87 times of Fy. For WSM method, 0.56 times of Fy. For LSM method, 0.87 times of Fy. Whereas maximum compressive stress, so which is nothing but it's provided at the compression zone. The stress created at the compression zone, which is nothing but in WSM method 130 Newton per mm square. In LSM method, limit state method, it was taken as 0.75 times of yield stress. But if the eccentricity is smaller, which is less than 1, so we are using as 0.77 times of yield stress. And bond strength, so already said that Fe250, it's a plain bar, there won't be much effects on the bond between the steel and the concrete, so there is no impact, it was normal. But whereas in the case of Fe415 HYSD bar, high yield steel deform bar, so the yield stress is 415, whereas the maximum permissible tensile stress 0.56 times of Fi, the same as we are using in Fe250, and that limit state method the same 0.87 times of Fy. So, and then for maximum permissible compressive stress, so 190 MPa, whereas Fe250 it is 130 MPa, but Fe415 it creates as 190 MPa. And for limit state method, the maximum permissible compressive stress 0.75 times of Fi, which is same as Fe250, but if the smaller eccentricity, it was getting lower than the Fe250. For Fe250 0.77 times of Fi, but whereas in the case of Fe415 it is 0.67 times of Fi. And the creeps, so it is having some deformed portions around the perimeter of the bar, so the bond strength getting creep up, so it is getting creep up of 60% higher, so 160% deformation getting resisted by the bond strength. Next one, for Fe500 grade steel, the yield strength as denoted in the numbers 500 Newton per mm square, and the maximum permissible tensile stress same as so what we saw in the last two types of steel. And in limit state method, so all the three types of components having 0.87 times of Fi. Then for maximum compressive stress, its for working stress method is 190 mm Newton per mm square, and for limit state method, so the same what we calculated in Fe415 grade steel, it's the same for Fe500 also, and it is also called as a deform bar. Hence, the bond strength gets creep up to 60%. So the bond strength here it's 160% than the normal strength which was creep in the Fe250. Another important factor for the design of reinforced cement concrete is development length. So development length is nothing but the length portion of the length which was incorporated into the concrete, that is called as developmental length. For example, so if you are taking this a beam, so this is a concrete, we are insert reinforcements, so RCC concrete, insert a reinforcement, the development length is called as this portion. The portion which was incorporated into the concrete is called as development length, and it depends upon some of the other factors also. Based on that only we are fixing the length of the steel which was incorporated into the steel. First one, size of the bar. So we have to specify which size we are going to use. Based on that, we have to provide clear cover as well as the development length and the permissible stress of the steel. So which was seen in the table that permissible stress in the tension zone, tensile stress, permissible stress at the compression stress. Based on that, we are selecting that development length. Other factor, the impact on one is bond stress. So based on the bond stress, whether there is a friction between the concrete and the steel, and if whether there is a proper bond in between concrete and the steel. So we have to first specify that. Based on that only, we have to keep the development length. The bond strength is given in IS 456 2000 in two pages. One page number 81 and page number 43. So for page number 81 is for working stress method and page number 43 for limit state method. Sorry, page number 73. Page number 73 for limit state method. So the bond strength depends on some of the factors. So the factors of bond strength is grade of the concrete, which grade we are going to propose, and type of the steel, whether we are going to use Fe 250 or 415 or 500. So which grade we are going to be designated in the particular location, and the zone of the concrete. So whether either tension zone or compression zone, we have to specify that where we are kept the reinforcements. Are you whether we are going to provide this reinforcement at compression zone, or we are going to propose the reinforcement at the compression tensile zone. So if we are proposing a steel at the compression zone, our bond strength become 25% higher. So when we are calculating the bond strength, our strength, normal strength plus 25% higher, we have to put it in the formula. Then the mechanical deformation, whether the deformation created after incorporation or not. So based on that, we are providing the we are calculating the bond stress and the friction between the steel and the concrete and adhesion between the how much the binding between the steel and concrete. All these six factors, which was taken care of bond stress. Next one, types of grade. Whether which type of steel grade we are going to be proposed. So we are having Fe 250, 415 and 500. So which type of grade of steel we are going to be proposed in a particular structural elements. Based on that, we are providing development length. And next one, zone of concrete. So whether then we are providing the concrete at tensile zone or compression zone, where we are going to keep the steel reinforcements. So if it is tensile zone, the length should be smaller. If it is compression zone, the length should be larger. And the last one, design, method of design, or whether we are going for working stress method or limit state method. So based on that, we are providing the development length. All these six factors which used to specify the development length in the particular structural elements. And for finding the development length, the expression was phi of sigma st divided by 4 into tau bd. Phi is nothing but diameter of the bar, sigma st the maximum permissible tensile stress, and tau bd is nothing but bond strength. So which was there in our IS 456 2000. So for example, if you are using Fe 415250 steel at limit state method, that LE development length becomes 5 into 0.87 times of Fi divided by 4 into tau PD. So which was we seen in the previous table. It shows that sigma is the maximum permissible tensile stress at limit state method 0.87 times of Fi. So we can substitute that value here, and value the formula become 5 into 0.87 times of Fi by 4 into BD. So for an example, if you are using Fe250 grade steel at the compression zone, so if we are the most probably this kind of problem might have asked in your competitive exam questions. So for example, if they are providing Fe250 steel in a compression zone, our expression become LD equal to 5 into sigma st 4 by tau by d. So 5 into sigma st 4 into, and we already seen that the zone of concrete, if it is provided at the compression zone, the bond strength become 25% higher. So normal bond strength plus 25% higher, our expressions become phi of tau sigma st divided by phi into tau bd. Whereas the same cases, if you are using Fe 415 grade steel or Fe 500 grade steel, our expression that bond strength becomes 60% higher. Our expressions become changes to phi into sigma st divided by 4 into tau bd plus 60% higher. So addition of 60% of bond strength, the expressions will be like that. Now we are seeing the exposure conditions, and that specifications are set of standards which was fixed for that exposure conditions. So if we are providing the structures in that exposure conditions, we have to keep this in mind. Based on that only we have to design. First one for mild conditions, so which is nothing but our residential buildings. So there won't be any rain waters or any kind of waters resist inside the our structure. So this kind of structure is called as mild exposure. So for this, that minimum clear cover. So there is a word called clear cover, which is nothing but there is a gap between the reinforcement and the end of the structural element. So that gap is called as that clear cover. So for example, if I am taking this as a beam, providing reinforcements at the tensile zone. So our clear cover will be denoted here. So this will be our clear cover. That the extreme end of the steel reinforcement to the nearest edge of the structure member is called as clear cover. So for mild exposures, our clear cover value should be 20 mm. So when if the diameter is less than 12 mm. So if we are using more than 12 mm diameter in a reinforcement steel, so we have to keep that clear cover as 15 mm. So the 15 mm is applicable for slabs. Nowadays we are proposing 15 mm for slab design purpose, and that minimum concrete grade what we are designated for mild steel is, mild exposure is M10 to M20. We can use M10 at minimum, we can use M20 at the maximum one, and the minimum cement content which is used for our specific mixed design purpose is 300 kg per meter cube, and the corresponding water cement ratio is 0.55, whereas moderate conditions, so it is nothing but the water storing structures is called moderate exposure. So whereas there won't be any current space and there won't be any coastal zones, there is a use of storage of waters, that kind of structure is comes under moderate exposure. So for that the minimum clear cover is 30 mm, and M20 at maximum, M20 is the maximum grade of concrete at moderate, and M15 is the minimum grade of concrete at the moderate exposure. M25 generally used for water tank designs, and the binder contains same 300 kg per meter cube, and the water cement ratio become 0.5, and severe exposure. So this is at the coastal zone areas, wherever some kind of tiles may be get and attack to the structure, and this kind of is called as severe exposure. So the minimum clear cover provided is 45 mm, and the grade designated in the corresponding severe condition is M20 at minimum, M30 at extent. The binder content is 320 kg per meter cube, and the water cement ratio 0.45. And very severe conditions, there was a structure which is built inside the spray of the sea level or inside the current. So in that situation, our clear cover become 50 mm, and our maximum grade M35, minimum grade M20, and binder content 340, and the water film ratio become 0.45. and extreme cases that irresistible chemicals attack to the structure is called as extreme exposures. In that case, the minimum clear cover is 75 mm and minimum concrete grade M25 and the maximum concrete grade is M40 and the binder container is 360 and the corresponding water cement ratio 0.4. Okay. So some of the assumptions followed were RCC structures which was guided at are given at IS 456 at page number 69 and 81. So some of the significant assumptions are the plane section remain plane after bending and the strain and the stress variations linear throughout the span. These two is the main assumptions in the IS 456 2000. Based on that, so if you are taking one beam, the depth of beam is capital D. So we are giving the each components which was discussed for design. So where T is the effective depth. So effective depth is nothing but that extreme end of the structural portion to the center of CG of the tensile steel is called as effective depth. Effective depth is called as T is called as extreme end to CG of steel in tension called as effective depth, and clear cover is nothing but that nearest portion nearest end of the reinforcements to the edge of the portion is called as clear cover, and as effective cover is nothing but the CG of the tensile zone reinforcement to the nearest edge of the structural elements is called as effective cover. And we proposed the stress diagram should be like this. The upper portion is called as compression zone and lower portion is called as tension zone. The upper and lower portions based on assumption should be linear. So here and here both the strain values are linear, and that conventional shear stress which was one is at the up to the centroid was parabolic, and from the centroid to the tensile edge it was rectangular in portion. This was conventional one, but based on the assumptions we thought that plane section remains plane after bending, so it was homogeneous and isotrophic, and upper zone and lower zone, compression zone and tension zone becomes common rectangular portion. Okay. So another important factor in RCC design other than that stresses is nothing but Young's modulus. So Young's modulus is nothing but a ratio between the stress and the strain. So here IS 456 2000 proposed that the Young's modulus of the concrete EC becomes 5000 root of FCK, where FCK is the characteristic compressive strength of concrete at 28 days. Well, the same case, the previous code books IS 456 1978 proposed that those EC is 5700 root of FCK. We still propose that in pre-stress concrete. In pre-stress concrete, we are proposing Young's modulus is 5700 root of FCK. And if the creep occurs in a concrete, so we have to find the effective Young's modulus, which becomes EC divided by 1 plus 5, where 5 is the creep coefficient. For example, if our 5 creep coefficient become 1.1, our effective Young's modulus become EC divided by 1 plus 1.1. So this is also you might have get in your competitive exam question papers. And as per American Code of Institute proposed that Young's modulus of concrete become 4500 root of FCK, which is 500 lesser than the EC value than IS 456. And modular ratio. Modular ratio is nothing but the ratio between the Young's modulus of concrete and Young's modulus of steel is denoted as modular ratio. More or less, this value should be minimum. In otherwise, if the modular ratio increases, the grade should be increased. For in empirical relationship, the modular ratio also derived as 280 divided by 3 into sigma B CBC, where the sigma B CBC value depends on 1 by third of FCK. So I already mentioned that if the grade gets increased, the modular ratio become down. So the grade, as per the grade increases, the rate of modular ratio become reduces, and the empirically it's called as 288 divided by 3 sigma CBC, where sigma CBC is the maximum permissible compressive strength of the concrete at the compression zone. Sigma CBC is calculated from 1 by third of FCK. FCK is characteristic compressive strength of concrete at 28 days, where area of the concrete which was derived from modular ratio, the expressions become AC equal to M into AST. AST is nothing but area of the steel in tension zone, and FCD, the area of the concrete at the stress of the concrete at tensile zone becomes should be lesser than equal to 0.7 times of FCK. Here, there are the three methods available for the design of reinforced concrete structures. So, which was working stress method, so short form is WSM, and ultimate load method, short form is ULM, and limit state method LSM. So here, the working stress method, the method which was proposed 100 years back, so it has an experience of 100 years. So in this method, we are taking only the safe loads. So in other words, it is called as design load. And the assumption, some of the assumptions carry out is the strain carry out at the steel, which is linear equal to strain carries at the concrete, and empirically the modular ratio become 280 divided by 3 sigma CBC. We already saw in previous, sigma CBC is nothing but maximum permissible compressive strength in concrete at compression zone, and the factor of safety is very high in working stress method. So here for concrete the factor of safety is 3, for steel the factor of safety become 1.8, hence our FCK become, that's why our sigma CBC is called it as 1 by third of FCK. So here the same sigma ST equal to 1 divided by 1.8 of Fy. So this is become 0.87 times of Fy. So 0.67 times of 0.67 times of Fi, which was we saw in the table. Next one, it's very good in serviceable conditions. So, but it is not good at collapse conditions. Why? The reason because we are taking only safe load. So even the load get excess due to some causes, some unfairness loads. It can't bear the unfairness loads, and the depth. While designed with working stress method, the depth of the structure become higher. This makes the design become uneconomical, and the some of the structures which is still used in our working stress method is RCC chimneys and water tanks. So these kind of structures still we are used to design the working stress method. And second one is ultimate load method. In 1950s, we have proposed some improvements in the working stress method, that is called as ultimate load method. So this method have very good safe condition against collapse, but not safe against serviceable conditions. So here the load, instead of that factor of safety 3, we have proposed some load factors, which was that 2.2 times of live load and 1.5 times of dead load. So, and the factor of safety for concrete here proposed as 1.81, and factor of safety for steel proposed as 1. And the stress diagram that become in working stress method, it become triangular one, but for ultimate load method the stress diagram become rectangular. And the already I said ultimate load method safe against collapse but not safe against service conditions. And the third one, which is nowadays very much of used in all sort of structures, is limit method. IS 456 2000 is only made for limit method. Some extents we can use for working stress method, but most of the things given in IS 456 2000, which was there for limit method. So here the both the concepts of working stress method and ultimate load method combinedly merges and given in ultimate state method so that it can bear both collapse load and service load. And the factor of safety for ultimate load design for concrete is 1.5, steel is 1.15. So then the sigma CBC becomes 0.45 times of FCK. And the thickness here, whereas working stress method, we saw that the thickness of the structural member or depth of the structural member is higher. But in limit state method, the thickness is lesser, but the usage of steel is higher than the working stress method. And the strain in bending compression should not be greater than 0.0035 in limit state method, and for direct compression should not be greater than 0.02. And if you are drawing a strain diagram in compression zone, sigma CBC taken as 0.0035, and for tensile zone the strain becomes 0.002 plus Fi divided by the factor of safety into ES. And the expression of XU is nothing but that centroid of the portion of the structure, so which is calculated by sigma cb, which is nothing but the strain due to bending at the compression zone, and divided by sigma cb strain created compression zone plus sigma st strain created at the tensile zone on steel into d. So this becomes, expressions become xu divided by d for Fe25 grade steel become 0.54, and for Fe415 grade steel XU by D become, can call it as XU max or XU limit 0.48, and for Fe500 XU limit divided by D equal to 0.46. Okay, up to this, that's it from today's introduction video. So, if you have any doubts, any queries, clarifications needed, can put it in a comment box. That's why I can able to clarify in the next videos. And please do subscribe. It was taking much efforts to making each videos. So I'm sure it will be useful. I hope also it will be useful for your preparations. And if you needed any further clarification regarding these introductions, so you can feel free to ask anytime. So I'll make another video, and those are preparing for IAS examinations. So in I prepared one video for that problems, and we'll try 3 or 4 problems, and we'll work out it which was asked in the previous IAS exams. We can solve this. You can have ideas as which kind of problems you may get in your IAS question paper. Okay, thank you. Please subscribe and give your feedbacks in a comment section. Thank you so much.